Okay, I guess we can start it. We have 10 or 9 here, or one TA, two over the Zoom. That's 11 students. Another two, they're going to take this online. So I think we have everyone here. Yeah, so it's a great pleasure to meet everyone in this class. So this is a very heavy loaded and fundamental course. You're going to learn a lot about electrical engineering and in particular signal systems in this course. And a brief introduction to myself. My name is Yi Zhou. You can just call me Yi. And I teach this course once per year, mostly in the spring semester. So we used to have a big class. Starting from this semester, we have 13 students. Yeah, and I work on, so my research is focused on machine learning, and in particular, I develop numerical algorithms for solving different machine learning problems. I look at theory. I also do some machine learning applications relating to signal processing or other general areas. So if you are interested in doing some research regarding signal processing or machine learning with me, you can feel free to talk to me, and we can discuss some research topics. Or if you want to learn something about machine learning or signal processing, you also feel free to talk to me. And so this is the syllabus. All the details are here. So that's my email. You can shoot me an email at any time. And my office is right on the third floor, right next to that long table. You can see a long table on the third floor. Class meetings Tuesday, Thursday at this moment, and the office hour. I put office hour right after the class, 2 to 4. Does this work for all of you? Yeah. But if you have any questions, you can always shoot me an email and schedule a separate appointment. So yes, and in this course, so this is a very fundamental course and very, very important course for the electrical engineering degree. Well, as you can see from this chart, and we are right here, 3500, called Fundamentals of Signal Systems. And this course will introduce all the concepts and technical tools that you are going to need for taking all these advanced courses. In particular, if you want to, in the future, you may want to take, if you are interested in robotics, you may want to take feedback systems. And this is signal processing with the digital signal processing, more advanced than the fundamentals of signal systems. And going further, you have this digital image processing. And that is related to, nowadays related to machine learning, artificial intelligence, all those stuffs. And digital signal processing, going further, you have all types of advanced signal processing courses. Estimation theory, if you want to design a radar, you may want to take that course. Advanced digital signal processing, and we have adaptive filters. So all these are very, very important and to design a mature signal processing system. And the other branch is digital communication systems. Where you want to design a wireless communication or other types of communication systems, you need to process all types of signals and discuss all types of systems over there. And then going further, you you will take the information theory course, which is another very fundamental but advanced courses, talking about informations instead of signals. And the other fundamental course that I think you may already taken is probability, engineering probability and statistics. You will need that. And then you take the random process, you can go to all the advanced courses. So basically, this course is really the fundamental of electrical engineering. We will learn we will introduce numerous types of signals. Basically, introduce the mathematical framework, and then develop a very rigorous and comprehensive theory to discuss and analyze the signals and their interaction with different systems. And going back to the syllabus, so that's the course description. Yeah, so this course is about 6 signal systems. We will talk about for signals, we will talk about all types of signals. And for systems, we will look at linear time invariant system. That is the very, very classical system that you will find in many real life applications. So I will not go over all the sentences here. But the course objective is to basically, the most important thing is to understand the mathematical language of signals and systems. So this course is a bit theoretical. You will need to play with a lot of mathematical formulas, doing a lot of calculus and calculating a lot of Fourier transformations. So the most important thing is to understand the mathematical language of signal systems in an abstract and also concrete way. And in particular, we will learn convolutions. Some important concepts are convolution. That is a basic operation for processing signals. So convolution is pretty much like multiplication in the number system. You want to multiply one number with another number. In signal systems, you want to convolve one signal with another signal. So that is a very basic operation. And then we are going to utilize this convolution tool to analyze a general system's input and output relationship. And then the convolution will also have a close connection to the so-called Fourier transform. So we will talk more details there. At the same time, we will also, in the lab sessions, we will also design and implement many different systems using the MATLAB. So the lab sessions are based on MATLAB based. You just need to have a computer and have a MATLAB installed. I think you can have access to the MATLAB. You can download it for free on the university's website. So make sure you have that on your computer. Yeah, we will also discuss, in the lecture notes, we will also discuss many important applications related to the concepts that and techniques that we introduced in the class. And the last one is about writing a technical report. So that is related to the lab sessions. So we have 5 labs. I will talk about that later. 5 labs, but for the last 2 or 3 labs, you need to write a short technical report. Yeah, I will give you a very standard template. It's basically like a short conference paper. You have an introduction, you have a methodology, and the results section, something like that. And these are the prerequisites. So basically, I think you will need to have a solid understanding of calculus and complex numbers. That's the two fundamental tools that you will need. Okay. So talking about grading, there are a lot of components here. We have homeworks, 10 homeworks, 20%, 3 examinations, 2 midterms, 1 final exam. Midterm takes 15%, final takes 30%. And they are non-overlapping. So midterm 1 covers lecture 1 to 4, 2 covers 5 to 8, final covers 9 and 10, I guess. And the labs, all the lab, we have 5 labs, so 5 lab assignments. They will take 20%. And I will follow this late submission policy. So first of all late homework submissions will be rejected. However, if you get into some situation and you need more time, you have 3 chances to extend the deadline for 1 week. Okay, you have 3 chances, but you must email me in advance. Email me and the TA in advance so we can accommodate on that. But other than these 3 chances, all late submissions will be rejected. And also the solution will be posted 1 week after the original deadline. So, yeah. So any questions? Not too. It only covers lecture 9 and 10. Yeah. But there will be some, I may put some bonus problems that, so those problems are bonus, but they are related to the previous lectures. Yeah. Okay, so this is the late submission policy. Make sure you understand this policy. All other than the 3 chances, all late submissions will be rejected. And the bonus, we have some bonus problems in the exams. You will see that. But the other bonus is course feedback 2%. That's at the end of the semester. For the quiz, I'm not sure if I can do that fairly, because some of you will take this online. But I will see if I can find a way to make some quizzes in class. So those will also be bonus. And in the end, this is the overall grading policy, grading criteria. Okay. I will strictly follow this criteria. I think you have the chance to collect a lot of bonus points in the exams, in the quiz feedback, and yeah. So I think over the past years, most students can get something around B+. And in fact, many of them can get A. Okay, so this is about grading, and we have 2 TAs. One is the lab TA, is Xiang. So Xiang is here.
We will meet on Wednesday and Friday.
Yeah, it's great to have Xiang here to help with the lab sessions. So we will talk about lab in detail right next. So Xiang will be responsible for the lab, for teaching the lab sessions and also grading the lab reports and lab assignments. The homeworks will be graded by Jia. And the exams will be graded by me. So I will take care of the exams. And the textbooks, we will use this signal system book by Obenheim and Will Speak. Second edition, you can get that on the Canvas webpage. But I think all the materials, the lecture notes and the homeworks, they are self-contained, so you don't have to refer to textbook. But you can definitely, I encourage you to read the textbook if you have time and put some extra effort on that. Some of the homework problems will refer to this textbook, so you can access to that on the website. The other reading materials is this book by Lathy, but again, I think mostly you only need to follow the slides, lecture slides. And all the lecture slides are available on Canvas. Yes.
The lectures kind of follow the order that
I think so. Yeah, I think so. So I think this will be a tentative schedule that we will follow. Yeah. Yeah, we will go over that later. So the exams will be announced in Canvas based on schedule. Yeah. Basically, after lecture 4, we have midterm 1, so you can you can kind of get an estimate from our based on our progress. Lecture 2 is after midterm 2 is after lecture 8. Final is after lecture 10. Before the midterms, I will give a review lecture, go over some problems, related problems. So there will be a review lecture and some review materials posted for each exam. I will also go over some of the homework problems if we got a chance in the class. And that's the tentative schedule. Basically, I think we have 9 bullets here. Yeah, lecture 1 is introduction lecture, but lecture 2 to 10, I think each one will follow one of them. So the first part is about signals. And then we talk about systems. And in the end, we combine them too. So that's the basic structure. Let me check. 7, 8. Oh, yeah. We don't have that here, but I think I'm not sure. I'm not sure what is chapter 8 about, but I think this covers all the materials that we need. Yeah. Okay, the most important thing here is the lab. So the lab is assigned to be, I think it's on Wednesday and Friday, 7:30 in person. But I want to discuss this with you. Is it okay to make the lab in IVC format, not in person? Which format do you prefer? Because the lab is entirely based on MATLAB. I think it might be more convenient to make it online, so you don't have to get up early and get to school at 7:30 in the morning. So I'm proposing to make the lab totally online plus IVC. So you just connect the Zoom, the TA will share screen. You will see a MATLAB, a screen with MATLAB and all the lab instructions. Yeah. No, it is entirely based on MATLAB. Entirely simulation based. All the lab assignments are also simulation MATLAB based. Yeah, so that's why I'm thinking of, I'm proposing to move it online plus IVC. And yeah, and I also propose to postpone the start time to be at 8 o'clock instead of 7:30. It's usually, from what I understand, so lab session lasts for 3 hours, 7:30 to 10:30. Most likely we will end in 1 or 2 hours. Yeah, so I think, yeah, so I would like to know about your opinion on that.
Could we still have to join on Zoom? Like maybe if a couple of students still are on campus, could we use the room to connect with Zoom? That will be, could we go reserve the one?
Okay, in person. Yeah, so that's the part I want to ask. How many of you would prefer the lab session to be in person? Okay. Okay. Yeah, in that case, we can still do in person plus IVC. So Sean, is that okay? Okay. But I think you may want to figure out how to connect to the projector, and also I'm not sure if you need to do it IVC, you probably need this cable. Yeah, so we can discuss this after that. And I don't think you need. Let me see. You probably don't need this electric board. Yeah, I think we will discuss this later. Yeah. So we can still do in person plus IVC. And I think the location is, I forgot the location. It's probably on the second floor. We have computers there, and I think the MATLAB is installed. But you can bring your own laptop. But for the starting time, is it okay that we start at 8 o'clock instead of 7:30? So we have extra half an hour to prepare for that. Okay. So I will change the starting time to be 8. And for the labs, you will each lab may take 1 to 3 weeks, depending on the materials covered. So basically, if the lab takes multiple weeks, in the first week, in the first 1 or 2 weeks, TA will go over the lab materials. And for the rest 1 to 2 weeks, those lab sessions will be basically office hours. Okay. Just no lectures there. You just work by yourself, and if you have questions, talk to the TA. And every lab assignment has a deadline sent to the homework. So you just submit the assignments. For the first 2 labs, there's no lab report. So you just need to submit the assignment. For the last 3 labs, you need to organize all your results, pictures, all kinds of stuff, put them into a short technical report using the template that I provided, and then submit the technical report and the assignments. So that's for the last 3 labs. And we have some grading rubrics for the technical reports, lab assignments. That is attached at the end of the lab materials. So for the lab submissions, the delay policy is that if you submit B days late, every late submission I will take 2 points from that. Okay. Any questions?
Lab start this week.
Tomorrow, starting right tomorrow. Yeah. You can attend either on Wednesday or Friday. Those will be repeated sections. Yeah, lab 1 is a pretty simple introduction to MATLAB. So I think you can finish the lab assignments in the lab session. Yeah, and cheating and plagiarism, I think everybody knows that. So basically, it's not allowed. If A copies work from B, then both of them will be punished for that. So I think this course, as long as you follow the materials and all the lectures, you will get a very reasonable grade. If you need any support, you can just email me prior to the exams, so I can give you some accommodations for that. Okay, so and for the labs, so because it takes 3 hours, and I strongly suggest that you make a good plan. Most of the lab assignments can be completed during the lab session. So I know many of you over the past years, many students choose to sometimes they will skip the lab sessions and choose to work on their own in their spare time, but often that takes much more time than completing all the assignments in the lab hours. So for example, lab 1, I'm pretty sure that you can complete all the assignments within 50 minutes. So you should try to finish that on Wednesday morning or on Friday morning. So that will save you a lot of time and effort. So I think the key of this course is on the homework part, on the lecture part. The lab is also very well developed, very important, but I don't want you to spend millions of hours on that, on the lab. Spend more time on the lectures, understand the mathematical techniques. Okay, so that's the syllabus. So, and what yeah. So the canvas, you can see. Yeah, let's go to the canvas. So everything is already on the canvas. Yeah. So that's the textbook. You can download it. That's the syllabus. You can download it. And these are lecture notes. So these midterms are now they are empty. But this is to remind you that there's a midterm right after lecture 4. We actually have 11 lectures, but I think normally we will not go there. We don't have that that much time, but I think you can, it's optional, you can read it by yourself. It's about filters, filter design. Yeah, homeworks are already here, so you can access to all the homeworks now. And also the lab materials. Yeah, I think that's pretty much everything I have. Yeah. So any general questions about the course?
Will we be able to use notes on exams?
Oh, yeah, that's a good question. Yeah. So yes. So typically for midterms you can take one paper, double-sided, take notes. Midterm 2, you can take another note. So you have 2 notes for midterm 2. Midterm 3, you can final exam you can take all. So basically you can take all the notes you have. Midterm 1, you can have one. The budget is one double-sided paper. This one is 2 double-sided paper. This one is, if you make another note, you have 3 double-sided paper. But yeah, you can feel free to bring your own lecture notes, handwriting notes. And in fact, I will provide some useful notes on the exam paper. So I think those are sufficient for the exam. So you don't really have to take your note, but yeah, I will let you decide. Okay, and your question.
For the, when we're doing the lab work, are we submitting it via the main course page and just ignoring the other Canvas section for this class?
Oh yeah, so you are always submitting everything through the section 1. Yeah. So I didn't even publish the other 2 sections. Yeah, I think this is easier to organize this everything here. Yeah, so okay. Other questions or concerns? Yes.
So this means for example,
Yeah, I will send the email maybe send the email. Yeah. So we will start at 8. Okay. So we have, oh, how many minutes we have? 12:25 to 1:45. Oh, we have 45 minutes. Okay, then I think we can start the. I don't want to show those mathematical formulas. Yeah, I need to. By the way, are there any questions over the Zoom? I almost forget that. Any questions over the Zoom channel? We have 2. Nope, nope, okay. So just give me a second. So I will always, this is how I do the in-person plus IVC format. So I will always show the slides on the left-hand side, and I have, at the same time, I have a Google Keep where I can take handwriting notes on the right-hand side. So basically everything will be on this screen. And then I will also upload the notes after each class. Okay. Yeah, okay, we can start the first lecture. Lecture 1 is actually lecture 0. Introduction lecture. We will talk about the background of this course, and at the end, we have a review section on complex numbers. Those are technical, but the introduction part at a high level. Yeah, so those are 2 parts. And this review of basic mathematics, they are very important for this course. Okay, so this course is about signals and systems. So let's talk about signals first. So typically we may think of signals as an information bearing quantity. So basically they carry information. They may carry some information. And if we can look at all these examples, we have radio signals. From those signals that can be decoded into into audio signals, and then you can hear from those sounds. Broadcast or cable TV, they are EM signals, electromagnetic signals. And audio signals, these could be electromagnetic or other types of signals. And in the circuits, we have a lot of voltage current signals, stock prices, images. And you can see that the signals, they exist almost everywhere in all types of forms. So in general, any physical or abstract quantity that can be measured or influences one that can be measured can be thought of as a signal. Light is a signal, and yeah. You take a picture of using a camera, that picture is a signal. And by the way, here I want to ask an interesting question. So, what is the difference between signals and the information? Or what is their relationship if they have any? Does one imply the other? Does one? How do you understand? How do you distinguish between these two? Yes, yes. Signals are used to carry the information, but if you think more about that, so how do you define the information? If you can carry if a signal can carry information, how do you define that? For example, if you look at the images, how do you quantify the information? Yeah. Yes. Yes. But I think those are techniques to generate your desired signal, right? You want to use some modulation techniques to put the signal in a particular band. So Yeah, this is a very hard question that takes human over 100 years to get a final get a satisfactory answer. So the signals are easier to understand because they are concrete. When we talk about signals, we know what they are. We look at the image, we know it's a bunch of pixels. We can describe them using a matrix. Stock prices, we look at the stock numbers. The signal is clear. Audio, video, every signal is clear. But the thing is that some signals may carry a lot of information. Some signals may carry no information. For example, if I generate an image with white noise, it's just all noise image. So you cannot learn from that signal. But if you look at this particular slice of the image, you can see a lot of information. There are a lot of texts and a lot of symbols. They carry some meanings. So if you take the well, if you take this course, information theory course, you will get the answer. So in this course, we talk about we describe what is a signal and how do we play with those signals in a rigorous, formal, mathematical way. And when we talk about information, it's a lot more abstract. We need information theory to describe information. Basically, information is we can measure information by looking at by quantifying its level of uncertainty. So that is a kind of formal definition of information. So information is the level of uncertainty. For example, if I tell you that, and if I tell you that I'm older than 10, my age is larger than 10, that is that carries little information because you can definitely tell that I'm older than 10. Now, if I tell you that my age is between 20 to 25 or 25 to 35, the uncertainty level is much smaller. So that will tell you more information about this particular person. So there you will, that's why we need this probability, kernel process, advanced probability. And in the end, we go to information theory. We need to use, in the end, people find that it is a great idea to use probability theory to describe, to quantify the information. And this is extremely useful when you want to analyze communicative systems, channel capacity, a lot of concepts there. Okay, and here are some signals that we will we have been seeing frequently in the field of electrical engineering. We have also, first of all, how do we mathematically define the signal? We define the signal as a function. Signal is basically a function of one or more independent variables. Depending, the variables would depend on the specific domain that we are looking at. We may be looking at a time domain signal. If we look at a one-dimensional time domain signal, then that variable is will index the time. So if we look at the image, then we may have the variables may index the locations in the space, the locations of the pixels in that image. And we also have frequency domain. So for example, if you look at this audio signal, this is a plot of a one-dimensional audio signal. These audio signals can be regarded as a function of time. So mathematically, we can write x parentheses t. X denotes the signal. We call the signal x. The signal is indexed by a time variable t. So if we want to look at the value or the value of this signal at a particular time, for example, if we want to look at what the signal looks like at t equals to 0, then you just need to look for x at 0. So basically, we describe the signals. In this case, we describe signals as a continuous time function. This is a function of time t. And in the bottom part, we have another example that shows a digital image. The image can also be described as a function. But here, instead of looking at, we don't have any time index anymore. So because we're looking at a static image. So the way we describe images is by pixels. We just need to specify the value or the color of every pixel. So because the image is takes a rectangular form, so it is very natural to describe the image as a function of two variables. Well, each variable, one variable indexes the location, horizontal location of all the pixels. One indexes the vertical location of all the pixels. Okay. So therefore, we can say that this image can be regarded as a function, and it has two variables m and n that indexes the pixel locations in this two-dimensional space. So for example, if we want to look at the value of this particular pixel, you just need to find out its locations, locations m and n, and plug in the values of m and n. This function will return that pixel value. Okay. Yeah. Yeah. That is a convention we call discrete signals, discrete time. But you can understand this as, so discrete time means discrete. You can ignore the time. So this time doesn't mean the physical time. It means discrete. Yeah. That's kind of convention. Because in the end, we throughout the course, we kind of divided the signals into two categories: continuous time and discrete time. But that time should not be understood as the physical time. It's just continuous, either continuous or discrete. Yeah, so these two are very standard for signals in a very standard form. We know, we have seen this type of signals in the, for example, in MATLAB. Many times we have seen these pictures made, and we know how to describe them, even without taking this course. But there are other types of signals that very special. So the previous examples are regular signals, which can be categorized into different categories. For example, we can say either they are one-dimensional signal or multi-dimensional. Right. This is one way to categorize them. This is a one-dimensional signal because we are looking at only one variable. But here we need two variables to describe it. So it's a matrix, two-dimensional matrix. Okay. Yeah. Okay, I will try to use I will use the mouse to point at all the materials from now on. Yeah. Sorry about that, and thanks for reminding me. Yeah, so the previous examples are pretty regular. Well, okay, one way to categorize them is by looking at their dimensionality, one dimensional, multi-dimensional. The other is what we just discussed, continuous or discrete. But we call them continuous time or discrete time. It's just a convention. And moreover, very interestingly, many now with the modern, for example, the data science, artificial intelligence, social network, IoT, all this fancy stuff going on, we need to encounter or address many newer types of signals in many practical applications. For example, the graph signal is a very popular and also very useful signal, in particular to model social networks or any other node-to-node interactions. So basically, in a graph signal, this is a visualization of a graph. You have many nodes, discrete nodes. Every node may represent a person, for example, in a social network, like your Facebook account. And then every of you may get connected to your friends, family members. So there's connections between these nodes. Right, and you can define many. All these contents are belongs to the signals. And in addition to this, for example, for every node, you may have some attributes. What is the gender, age, race, etc. All this information can be attached to every node. So those information also belongs to this graph signal. And moreover, you can just simply, this can be made very, very flexible. Sometimes you can describe the relation, the close of the relationship between two persons by specifying the strengths of the connections. If one connection is if the relation is very close, then maybe the connection can be visualized by a very thick line. Otherwise, if the relationship is not that strong, we can describe it by a very light line. But so here's my question for this signal. This is a non-typical signal because for the other signals, we know how to write them. This audio signal is indexed by time t. For this one, it is a rectangle, so we know we have x, y, two axes. Now for these two axes, we can use two variables to index them. Now my question is, how do we mathematically express the connections between all these nodes in a graph? Because we don't have you cannot find an axis here, right? You don't have a time axis, you don't have a space axis. It is not flat, it is very complicated. All the nodes are it's a messed up here, basically. And sometimes with some fancier tools, we can visualize this in three-dimensional space. But in any way, the graph is it's just not regular. So can we find a way to characterize the relation the connections in this graph using the mathematical forms that we, for example, we have seen here. When we define the graph as a type of function. So the important thing is that we need to find a certain basis or axis for describing the signal, right? In the time domain signal, we know that it's very natural. We describe the signal over time. So t is what we are looking at. And then we can look at, okay, what is the value of the signal at every time step. For the images, it's rectangle, also very natural. We just look at describe image pixel by pixel, and every pixel is indexed by two numbers on the two axes. So the important thing is to identify a type of axis. So looking at this graph, what do you think could be a proper axis for describing the graph? Apparently, you cannot just look at this picture, right? It is just a visualization. You can visualize it in two-dimensional or three-dimensional. For example, with this two-dimensional visualization, if you describe it using x and y axis, it is not reasonable because you can just move the graph around, so the locations will also move, but all the relative connections and the relative relationship among all the nodes will remain the same. So that is not a good way to describe this graph. So the important thing about this graph is well, you can tell is the nodes, the persons, they are the fundamental elements that constructed the graph. So for a graph, we can try to describe it as follows. We have, for example, we have let's say we have multiple persons involved in this graph. How many of them? Let's say there are n persons. So we have n nodes in this graph. How do we describe this graph? Basically, we want to find a function so that we can reconstruct this graph from that function. So one way to do that is basically to reconstruct graph. We just need to have two things. One, I need to know how many nodes are there in the graph, so that I can put the correct number of dots in this picture. The second thing is that I need to know their relationship so that I can connect these nodes in different pairs accordingly. So we can just generate a table, two-dimensional table. So the idea is that this table will list all the possible connections, pairwise connections among the nodes. Right? We have this one, two. If you look at the first row, it is basically characterizing the relation between the first person and all the other persons, including herself. Looking at second row, characterizing, we can use this to describe the relation between second person and all the other persons. So what we just need to do is to in this entry, blank entries, we just need to, for example, we can say 0 means not connected. But looking at this graph, if two nodes are not connected, we can put a 0 there. If they are connected, we can put a 1. And then you can just fill in all these entries by looking at the graph. In particular, this diagonal line will always be 1 because one person is always connected to himself. And the other thing, we can just fill it by looking at the graph. So we call this the adjacency matrix. So the nice thing is that given this table, you can draw a graph correspondingly. Right? And given a particular graph, you can always encode the relation, the connections by using this adjacency matrix. So in the end, you can say that this is a function. Well, it's a function of two variables. Because this table is a matrix, you have x and y axis. But these two variables, both of these two variables indexes the nodes of this graph. Okay. So this is we can see that even for these unregular signals, we can find a way to describe it using functions. So that's why functions are general enough to describe all types of signals. And in this course, we will introduce a very fundamental tool, that is transformations between different views of the same signal. So in particular, we are going to look at a particular signal in different domains. One example that we will see in the lectures is that we will try to describe. So in the bottom, so in this figure, right, in the bottom part, this is a signal of interest. Right? For example, we are interested in this signal. So there are multiple ways that we can look at this signal. The first way, a very standard way, is we can look at the signal in the time domain, so that from this figure, we know that at a certain time, we know what is the amplitude of this signal. That is one way of looking at this signal. But then you realize that usually this signal, many signals looks like sinusoidal waves. They have a lot of fluctuations. So looking at the signal time by time may be very complicated due to these fluctuations. But at the same time, you can sort of see some periodic structures in this signal. So therefore, that's why we will introduce the Fourier transform to describe this signal in a more efficient way. Now here's the one example that how do we do that? So in Fourier transform, basically we will decompose this signal. We will decompose this signal into a summation of multiple sinusoids. And in this picture, the first three pictures, top three figures corresponds to these three sinusoidal signals. It turns out that the bottom signal, which is the signal of interest, can be decomposed into these three sinusoidal signals. And the nice thing is that these three signals, they are periodic. They take a very standard sine form. So this makes much easier to understand this signal. So we just need to know that the signal is located at three different frequencies. That's the key information. So in that way, we can describe such a complex signal in the frequency domain using only three dots. Yeah, and do you know other examples of transforms? Any other types of transform that you can think of? Laplace transform. Yeah, we will also talk about that at the end of the lecture. Yeah, Laplace transform is a generalization of Fourier transform. But in general, there are tons of transforms in the field of electrical engineering. In particular, if you take the image processing course, there are numerous transforms there. I think the central idea of transform is that, so first of all, no transform is universal in the sense that every transform is convenient to use for only a small class of signals. That's why we need to develop millions of different transforms. Every transform has a particular application domain. For example, if you look at Fourier transform, like in this example, because the signal takes a sinusoidal form, so it is very convenient to describe this signal in the Fourier domain. By doing a Fourier transform, we know that it only has three Fourier components. So that's a very efficient way of describing this signal. But then later you will learn that, for example, if we want to describe later we will introduce a signal called impulse signal, which is basically this, we call it delta t. Delta t, what is signal? Delta t, how to describe this? Delta t equals to 0 for all t not equal to 0. So that means everywhere else, the signal is empty. But at this original point, this signal has an infinite amplitude. That's how we formally define this signal. Taking integration around this original point of this signal, we get 1. So that means that essentially means that at this original point, the signal must have an infinite magnitude. Otherwise, you cannot be integrated to 1. If you do a Fourier transform of this signal, you will see that in the spectrum domain, it is everywhere. It's a flat spectrum spreading over the entire frequency domain. So that means you need endless Fourier components to describe this signal. So meaning that Fourier transform may not be efficient to describe the signal. Instead, looking at the time domain is already very efficient because the signal only locates at the time at the original time point. Yeah, but in this course, we focus on the Fourier transform as a very important example. And in particular, when we do a Fourier transform, later on we will be more specific. We are going to transform a signal in a time domain into a frequency domain. So why do we choose frequency domain representation? Because it turns out that many signals has close relations to sinusoidal-like signals. That's why, therefore, the Fourier transform is very efficient for describing these signals. By taking the Fourier domain representation, we can reveal the fundamental characteristics of a signal system. And many systems, in particular linear systems, they are much easier to analyze from this frequency perspective. So instead of looking at very complicated signals in the time domain, it is very efficient to analyze them in the frequency domain. And besides signals, the other component that we are going to discuss is systems. So the system is used to, as shown in this bottom figure. This is a standard system diagram. You have an input signal to the system, and then on the output side, the system will generate something else. And we have many systems in practice already, like mobile phones, cell phones. When you make a phone call, but if this is a cell phone system, then when you make a phone call, you will receive some electromagnetic signals over the air. Those signals going into the system, will decode the system and decoding the signal, and then translate them into audio signals, into sounds. And then you can hear those sounds from output side. So this is a very standard system. So in an abstract way, a system is basically a black box that characterizes the input and output relation for a particular type of signals. For example, university can be regarded as system. The input is a new student, freshman student. Output is the graduate student. This is already a highly nonlinear system. And this is a very typical example of communication systems in electrical engineering. And this system, if you take the some more advanced courses about communication, you will learn that the system includes multiple standard components. For example, you want to control a robot on Mars. You have a robot on Mars, and you're going to send a signal from the Earth. How do you do that? You are going to build such a communication system. Basically, you have a message to send, a command. This command, you will need to encode the command. Okay. So in the first stage, you are going to send a message to the transmitter. Now, here the transmitter is the antenna. But this step is already non-trivial, because think about that. If you want to send a 0 to the robot, it is likely that this signal will be distorted over the channel. So when you encode this message, you need to think of a way so that the message is robust to perturbations or distortions. So the easiest way But the most straightforward way is to repeat the same message multiple times. Right? Instead of sending 1 0, you send it 100 times, and hopefully less than 50% of them will be distorted to 1. And at the receiver side, you can do a majority vote and decode the original message. But then you will have to transmit a long sequence of repetitions of messages. That is very inefficient in many perspectives. That's why, so this issue, you will learn how to address this issue by taking the information theory course, coding theory, how to design some coding strategies to decode the message. And then you send, okay, now you send the final message to the transmitter. The message is encoded in a way that is robust to the distortions in the channel. Antenna send a EM signal. Now the antenna send the electromagnetic signal, send out the EM signal. So what is the channel? Channel is all everything between the antenna and this robot. So it includes the atmosphere of the Earth. But the EM signal first need to propagate through the atmosphere of Earth. This will create a lot of distortions, a lot of noise. Then going through the universe. Finally, it arrives at Mars, going through the atmosphere of the Mars, and finally arrives at this robot side. So everything between them is regarded as the channel. And this channel can be highly dynamic depending on the atmospheric conditions. Some days it's sunny, some days it's cloudy, rainy, different weathers, the channel will be totally different. Okay, and then finally the robot receives something from the receiver side. It needs to decode the message in a proper way. So if you encode the message in a smart way, the decoding now on the decoding side, hopefully the message will be decoded correctly. So it will receive the correct command. But of course, you always have some probability of error. You have some probability to receive and decode the wrong message. So in the end, you need to decode and estimate the message. So whenever we talk about estimations, there are always a probability of error. Yeah, and there are, so previous example is a very regular example, communication systems. Again, in the modern machine learning or data science field, we have a lot of artificial intelligence systems. They are not physical. They are all described in the software programs. By looking at this, for example, looking at the first classification system. You have a system described by a neural network that is all the layers in the middle, very complicated. But what does this system do? It takes an input image. That's the input. You can input the image. Now you train the system so that it can classify the image in the sense that on the output side, it will tell you that this is a cat. This is a classification system. But in general, you can use these neural networks to do all kinds of fancy stuff. Everything that you can think of. In the bottom, this is another system to generate captions for a particular image. Yeah, you can see this in a lot of social platforms. So basically, I think nowadays, if you take a picture using an iPhone, after several days, the iPhone will automatically generate a short sentence to describe the image. For example, I went to Las Vegas for 4 days, taking a lot of pictures. After 2 or 3 weeks, it automatically generated a story for me. And with a caption saying that this is dinner at Las Vegas, I was totally surprised because all I have done is to take those pictures. So for that system, the input is a blank image, and then the system will generate a sentence depending on the content of the system, generating a proper sentence to describe it. Of course, for both of these artificial intelligence systems, you need a lot of data to train, or we call training, but that means to fine tune the parameters of these system models. Yeah, so this is about artificial intelligence systems. They are driven by the big data. Yeah, so I think this is all the introduction part about the lecture 1. So in the next, on Wednesday, on Thursday, we're going to start to talk about review some complex concepts about complex numbers. Okay, this is very important for this course. Okay, so I will stop here and I'll see you all on Thursday. So don't forget, tomorrow we will have that lab session at 8 a.m. I will send an email right after this.